Okay, good morning everyone. Welcome to the GISS Forum 2025. And we will start soon. But to let you know, we are also testing live on GISS, YouTube. So everyone in the world is watching. And also we will post the video, some of them on YouTube channel. And also some presentation will be available for pay-per-view for each one after the meeting. So let's enjoy today. And this is the tentative final program. It may be flexible during the day, but we will follow on this. We will have the key session will be the award ceremony before lunch. And after lunch, during lunch, we will guide you for lunch and come back for more presentations. And I will review the pricing of the new products at the end of the day. So let's start.
Hello, I am Merton Flemings, and it's my pleasure to once again welcome you to the GISS Forum 2025. Every year, it is inspiring to see how this community continues to grow and push the boundaries of GISS technology and of sustainable die casting. So far, we have shipped more than 160 GISS units to 16 countries. And this forum is more than just an event. It is a platform for exchanging ideas, building partnerships, and accelerating industry transformation. I encourage you to actively engage, to challenge ideas and explore collaborations that will shape the future of our industry. Thank you for being a part of this journey, and I look forward to hearing about the exciting discussions and innovations that will come from GISS Forum 2025. Best wishes, for a productive and inspiring day. And thank you very much for inviting me for this part of your meeting. Thank you.
Have you ever noticed how much of our world is built with aluminum? From the frame of your phone, to the gearbox in your car, to parts flying through the sky in airplanes, die-cast aluminum holds the modern world together. But behind its strength lies a hidden cost. Many aluminum die casting plants melt and hold aluminum above 700 degrees Celsius. This process alone burns massive energy, emitting several million tons of carbon dioxide each year, on par with the entire manufacturing footprint of a small European country. And there's another problem. Fast-flowing molten aluminum traps air, causing porosity, tiny defects that weaken parts, increase waste, and generate even more emissions. But there's a better way. Introducing GISS technology, short for gas-induced superheated slurry. Instead of melting and holding aluminum at high superheated temperature, GISS gently stirs the metal with fine inert gas bubbles at a lower temperature, typically below 620 degrees Celsius. The result? A superheated slurry that flows more like warm milk than water. Smoother, calmer, more controlled. It fills molds with less turbulence, fewer defects, and lower stress. That means stronger parts, less scrap, longer mold life, reduced spray and water treatment usage, shorter cycle times, and significantly lower energy consumption. In fact, switching to GISS could cut around 3 million tons of carbon dioxide each year. That's the same as taking 1 million cars off the road, shutting down 5 coal power plants, or planting 200 million trees, enough to offset the annual carbon footprint of approximately 500,000 people. GISS isn't just an upgrade. It's a breakthrough, where precision meets sustainability, and progress no longer costs the planet. Because how we cast aluminum today shapes the world we live in tomorrow, let's cast it wisely, with GISS technology. Have you ever noticed how much of our world is built with aluminum?
Welcome to the world of metal casting. Good morning, everyone. My name is Jesada Wanasin. I'm now leading 2 missions. One, GISCO, we make the casting world better. And Colorless, we save the planet. And I'm also an associate professor at the Science Park Prince of Songkhla University. Today, I will explain GISS as the superheated slurry casting process. For thousands of years, we have been casting metals the same way. We melt metal completely. We pour it while it's superheated liquid. And we hope it solidifies in the shape we want. But there is a problem. It traps air and it forms defects. And when it freezes, the structure becomes non-uniform. It's like baking a cake at too high a temperature. The outside burns and the inside stays raw. Everyone in the metal industry has lived with this problem. So we ask a very simple question. What if the metal doesn't need to be superheated liquid? What if there is a new state of metal? Not superheated liquid, not liquid, not slurry, and not semi-solid. Something in between. We call it superheated slurry or GISS technology. So what does that mean? Imagine hot water with tiny crystals of ice particles inside, a meta-stable state. Not frozen, not boiling. Just balanced. We can do the same way with metal. The metal transforms smoothly from warm milk to milkshake. And then to ice cream. During the GISS process, we gently inject inert gas bubbles through a porous probe for a few seconds. The gas doesn't mix into the metal, it simply controls how solidification begins. When we understand this principle, we can control the structure of the metal itself. And when we can control it, we can change everything. Today, you will hear more from my partners. Mark over there. Mark, push. Tommaso, Botto, here. John Ford. Yu Feng He. Chu Jian, right? And Hu Lijun. And here are my final remarks. At GISCO, we believe in sustainability, collaboration, and partnership, success and sustained happiness through collaboration, environmental, social governance. I hope you enjoy our GISS Forum today. Thank you. And the next presenter. Please welcome Mark.
Yeah, welcome everybody to my presentation. Thank you, Jess, for the invitation. It's an honor for me to already speak the third time on this nice forum. I followed the GISS development since many years. During my study and my time at Bühler, I made several analyses of different semi-solid routes. I also even had experienced the Tixocasting, the very first semi-solid process when I started as a young engineer in Bühler. And it's just amazing to see how GISS is developing and showing all the benefits and the easy application. So today in my speech, I want to focus a little bit on the economic part of GISS. And I want to show this with some hard samples, with hard facts and figures. So if you move on with the presentation. I give first a short introduction to myself, then I want to show or highlight a little bit the benefits that I see from the process, and then I want to show you my cost calculation tool that I developed when I was as a young engineer. I started in Bühler. I developed a return on investment calculation tool, and this has been used many years. Still today in my consulting field I use it to help customers to make their strategic decisions. And I then apply this calculation tool on 3 examples that I followed with Jess, and I want to show you that today. That's the other way, huh? So my name Mark Fuchs. I was like more than 10 years in Bühler die casting Switzerland. There I had several leading roles. I was head of application technology. I led more than 40 engineers worldwide. Then I was like 5 years head of product management and marketing. Also here I had like 6 employees worldwide for the business area die casting. And then for like 3 years I also headed the department of sales. Also here I was responsible for a yearly order intake of about 400 million Swiss francs, the size of Bühler die casting, when I left at that time. I also went into the foundry business itself, so for about 8 years I was also producing die casting parts. So I'm not only in the field of die casting machines, but also applying the machines to produce components. So I had 2 companies, one in Switzerland, Wagner, and then Wagner Bosnia. That was a joint venture with Wagner Switzerland, where we focused mainly on electronic housings. And there I had many years head of engineering and sales. Then about 3 years I was the CEO, and at the end also in the board of directors of the company. Then I also had a job in the Swiss Foundry Association. I was responsible for the public relations, and since about 2 years I'm doing some consulting for the die casting industry. Beside my other job, since a few years I started the field of chocolate. So as a Swiss you also have to, stick to the roots. I'm now also in the chocolate machinery business, but that's just a side note. Benefits of GISS. I talked last time already. For me, this is the most easy applicable process into existing processes, be it horizontal cold chamber die casting machine, be it gravity die casting, be it vertical die casting machines. I think the applications are almost unlimited. It's so easy to apply, and you can immediately see the effects on the benefits. So that's one thing for me. Then the Professor Flemings mentioned it's over 100, I think it's 160 or 170 at the moment, already sold units to the market over many years. I think that's a clear hard fact that GISCO is in the semi-solid forming established and well recognized. We have many customers who are repeatedly ordering units. Again, as a strong sign that this process, this company is now has reached its targets, I can say. You have come to recognition, I can say, in the market. What is also nice, and that's the fact that we don't go really into the semi-solid state. We are applying above liquidus, so any kind of alloys are possible. And this gives you a complete new range of application, of new components, of new alloys that you can apply, and that you cannot do with any other semi-solid processes. So you cannot really compare GISS to any other semi-solid processes. It's a different animal. Again, I already mentioned, for me, it's the most compact and efficient solution on the market. It's easy to apply. You immediately see the benefits. And that's not easy when you look at the other available processes. You have heavy investments. You need to change the cell. You have to, you have to completely rethink the automation. And here you can apply it, you can use it, or you cannot use it. So it's really, really easy and simple to apply. And what is good, it solves most, I would say, most of the conventional problems that we have in liquid die casting. It reduces shrinkage. As you have already some particles in the melt, the shrinking volume is less. And you can also go to slightly smaller machines. Also, this has been proven in the past. As the metal is already partially solidified, you have basically less projected area. You can go to slightly smaller machines. You have higher tool lifetime. Here are many examples showing in the market that, I don't know, I think the maximum we have achieved is like 2.5 or 3 times the original lifetime, so that's crazy. We have, of course, less soldering. We also have, due to the defects, gas porosity, shrinkage porosity, we have a lot of limitations in the mechanical properties, even if the alloy is good, but the process itself, due to the grease of the piston, due to the spray lubrication, you have defects automatically. And with this process, you can reduce that massively. Then die casting is heavy investment. The tools are expensive, the machines are big and are heavy, are expensive. If you apply GISS, of course, you add an additional investment. We will come to that later in a first step, but when you experience and you learn from the process, you realize that you can go down to a little bit smaller machines. And then on the long run, I think also here you will save. You will save money in investment, you will save money in tooling, and that's why it should be not red, but in the beginning, of course, it's an investment in the technology, but over time you realize that you can reduce the investment, you will save money. Yeah? And then gas porosity, of course, here also, you still have the piston, which needs to be lubricated, but you can do less, because you have less heat impact. And over time also here you can optimize your spray lubrication, you can optimize your piston lubrication, and that also gives you better quality of the casting. But in the beginning also, of course, here gas porosity, if you don't change the process, you just apply GISS, you will not on the first run see the benefits. It's a learning curve. So it's not just the installation and then you have immediately all the benefits, but you can step by step tick off this benefit we have achieved. Next, we're working on optimizing the process, and then you gain the next benefit. So it's a journey. You have to apply, you have to understand the technology, but you can reach all these benefits over time. So I want to show you the financial benefits of all these just mentioned samples on 3 examples. So I selected 2 parts on the left, which are real parts in production with GISS. And you can see the left one is a brake housing, which has porosity problems, leaking problems. It's a 2-cavity mold on a 400-ton die casting machines, and the lifetime was set to 100,000 shot of the die. Cycle time is about 55 seconds. Then in the middle we have a heatsink, a typical component which is already optimized in die casting, so good cycle time. Shot weight or the part weight is about 800 gram. It produced on a 400-ton single cavity. Also here the calculation was 100,000 shots. And the cycle time was the same like the one on the left. And then the third one is a more theoretical part. I was in discussion with a Swiss structural component supplier. I don't want to mention the name, but it's just around the neighborhood, having factories also in China and in Czech, and is producing those parts here for Mercedes. And I was also in discussion with him in my consultancy to apply GISS for these structural primary alloys. And I showed him all the benefits that he can gain based on the assumptions that we took, what benefits can be achieved. So before I go now into the real benefits, I want to show you quickly my calculation tool. So if you could please open the Excel file. I don't want to bore you too much with the details, but just to show you that how the tool is set up. So on the first page, you go into the comparison. So as I was working for Bühler, of course, I had all the cell details on the left side, but basically at the end, you have on the top right, you have the price of the installation, which you're comparing, the ground occupation, so how many square meters you need, the electrical power which is installed, and then you have the comparison installation. In this case, I was comparing a Bühler cell against a competition cell, which was cheaper, but less performant. The ground application was more or less the same. The electrical installation was almost the same. And then here you can put in the price of the component, to which price you think you can sell that component to the market. Here is the depreciation of the cell and the annual interest for the money that you need to loan. So and if you go to the next, exactly. So here you put in the typical values that you are using in your factory. So how many days you are producing, how many hours, how many shifts, how much is the cell used for this specific cell. Then what is the utilization rate, the availability of the cell. Here I was assuming that the Bühler cell was like a little bit more stable, more robust, so 2% higher OE compared to the competition. And as we are applying at that time microspraying versus conventional spraying, the cycle time also went up. That means more output. And we had like 10 more shots compared to the competition cell. We had 2 castings and twin cavity, and the reject also was less, as we had nice squeeze pins. And the joints where the helicoils had to be put in were always problematic with porosity. And that we showed that we can reduce, so the scrap was reduced by 1.5%. And then we move on maybe to the cost. Here you can put in how much cost is the first die, the second die, the inserts, the trim tool, what is the cost for the machining, what is the cost for the alloy, the melting, the secondary recycling cost, so all the, of course, the needed value inputs that you need for the cost calculation. And then if you put in all that, you can come to the final cost. If you go to cost per part on the right side, then you see the final cost in detail. You see here, for example, on the left side, the 28 euro per castings versus 30.7 on the competitor machine, with all the details split with the metal, overhead, etc., die costs, etc., etc. And if you go now to the payback, you see here the higher investment of like 600,000 was amortized or paid back already after roughly 9 months. If you go down a bit, you can see the numbers. I know. Doesn't show here. No. Normally we have also some numbers here. And then after lifetime, you see that the amount of money that you are saving over time. So that's the tool, how it works. And here, maybe on the break even as the last, it shows also, depending on the price that you set and the costs that are generated in production, how much time it takes until your break even is given. And from that point on, you start earning. You start earning by selling and producing those parts. So that's how the tool is set up. And now maybe we can go back to the presentation. If you go to the next slide, please. So I start with the first component. As I said, this was a problem that the scrap rate was crazy. The customer had to impregnate a lot and throw away components. And by applying GISS, the smallest unit, 100,000 euro investment for the initial unit. Then of course also the probe, the graphite probe, doesn't last forever. You have like 100,000 seconds of dipping time, and then the machine tells you, and now you should replace with a new proper probe. So of course you have to calculate that in. Then you add of course the GISS units, the control unit takes a little bit of energy, that's clear. And also the nitrogen or the inert gas consumption needs to be calculated in. These are add-ons which are of course, yeah, having some investments that you need to consider. But on the other side you have benefits. In this case, we could increase the lifetime by 50%. We could have massively reduced the cycle time by 1/3. The scrap was, almost gone. No impregnation anymore, no waste. And of course, you have a much more balanced thermal management on the die. You have lower temperature on the holding furnace and less energy input on your thermal management on the die. So this overall was calculated and factored in, and you can see that this project would have been a killer for the organization. So this was a saver. Without GISS, either the company would have gone bankrupt or he would have stopped that contract. So that would have been a disaster if he would have continued with the existing production. That's I would say this was an enabler to continue this production. And you can see over, I always put 2 million because to give you a comparison of the 3 samples, in this case, over the 2 million shots, 27 more million savings. So you can imagine this would have been a killer for the organization without applying a GISCO technology. This, of course, is an extreme case. No? Of course, you can always discuss, but die casting has always problems. There are other means to solve problems, but this is really an easy application, and you immediately benefit of all these factors I just mentioned before. Then the second component. This component, you have to imagine, these are components which are in the market since many years. They're optimized they are fine-tuned. Every year you have to give ratios. You have to come down 3%, next year 3%. So this product was already optimized. And also here we applied the small unit, 99,000. Also the same parameters like before, but a single cavity. Not the 2 cavity, but a single cavity. And also here we were able to increase the die life 50%. In these typical components, you have a lot of issues with ejector pins. You have the holes for the self-drilling screws. You have the flatness. You have the areas where the ICs are contacting, so you are not allowed to have any pickles on the surface. So very sensitive areas to transfer the heat from the electric port to the housing. And also here we were able to slightly reduce the cycle time. We had less stoppages to the die. We were achieving the same quality, so there was no big impact on quality improvement. And also here we had the lower furnace temperature and the thermal balancement, which of course also factored into calculation. Here the cost, you can see it's not huge difference. It's like 20 cents, but over time you can see it took us, for the investment of 100,000, it took us something like 17 months to pay back. And over the 2 million as a reference, it's like 300,000 more gaining. So you can say that's not a huge amount, but it's also good to get new orders. So it makes you more profitable, more competitive to the competition, so you can gain more orders against your competition. So, and I think when you look at the development of the costs of this component and then adding GISS, it was like a new step, a step of improvement. Okay, I showed you now an extreme component and a more average component, and now I want to show you some future potential, as I discussed and told. Here, of course, we have to apply a bigger unit. Now here the investment is also slightly higher. Yeah, and also the probe cost, of course, are a little bit higher than the small machine. And also, of course, you have to consider the electrical installation and the nitrogen consumption. I was assuming here also a lifetime a die life increase of 50%. I was assuming, as we had the 3% from the smaller component, that we would also have 3% cycle time decrease. Also here, similar problems. I mean, it's a thin walls structural component, but just on a bigger machine. Less die problems, 2%, and also less problems with the joints where the helicoils have to be put in. So you have to machine, you have to put the helicoils in, and this is always the area where you need attention. And again, here, lower energy, and if you factor this in this component, you can see it's around 1.7 euros per casting difference. And I mean, the investment of like 240,000 is amortized in less than 10 months and gives you a huge amount of savings after the 2 million of components. But again here, you have to make the step. You have to convince the organization to apply the technology. It's not just a simple add-on and then it runs. You have to commit, you have to have the team, you have to understand the process and then go in, and then you will benefit of this just showed figures. So I encourage you all really to not just dictate and say let's do it, but you have to define a team who's going after it and stick to it. And then you will, I'm sure, together with GISS and the team, you will be able to improve your profitability of your foundry. So with that, I'm finished my speech, so I'm open to get some questions. Thank you very much.
Quick question. Well, you mentioned for the lifetime increase of 50%, right?
Yep.
So what's the principle, your calculation for this lifetime?
It's not a calculation, it's real data.
Yeah, I know for this GISS technology, you will increase the melt temperature, right? But for the
decrease. Yeah,
decrease the melt temperature. But for the injection pressure will be very higher than normally die casting process. I'm not sure. Can you get my point?
It's reduced. So you have.
Yeah, injection pressure will reduce.
Yeah.
Why is it increased? What do you think?
Okay. Yeah, maybe I can check offline.
Later we will talk about the.
No, the flow behavior.
Okay.
When it comes to the end of the filling, especially, you don't need this typical heavy shot. You know, this typical die casting third phase where you make a big fuss to feed the melt into the last corners of the cavity. It's a very smooth filling.
Okay, so for next session you will introduce further. Okay. Yeah. Okay. Thank you.
The die life has I think has several impacts. You have the delta T. You go down with the melt temperature, and the die temperature slightly is higher. So the delta T every cycle is not that crazy, but is reduced, and also the mechanical impact of each shot is less. And this overall, I think, gives the benefits, but maybe Yufeng will go into more details then. No? Yes, please.
Mark, just one question. You mentioned that tonnage of the machine also reduced. Did you consider the benefit of that also in your financial calculation?
No.
Oh, that's the additional benefit on
Yes.
the capex reduction.
Yes. We assume that in standard horizontal die casting, depending on the component, you can go down to like 25 to 30% less tonnage.
Okay, thank you.
Yeah.
Any more questions?
Okay. Thank you. Thank you very much.
I think we will go to finish. Okay. Coffee break. Okay, have a rest and come back. Maybe 10 minutes we start so we can have early lunch together. Okay, see you in 10 minutes. Thank you.
พี่เดี๋ยวจะขอเขาลงสไลด์อะค่ะ
John อ๋อเขามาเสียบเลย
อ๋อเสียบเลยใช่ไหมคะอ๋อเดี๋ยวเราขอ
You want to test the slide?
So you're gonna use your laptop, right? No, not transfer the file, right?
Transfer the file.
Yep. And do you have any video?
Some video, no audio.
Audio. Okay.
和模具寿命，要不然你一堆挂包机，你抛光你抛，你又受不了。15000的时候，那再能扎实，因为是小，针线那么大，无论你怎么使用，使用最好的钢丝，你可以做的实验从3万，所有情况在3万的时候，它都有效果。就是我有没有实现？那当然，我刚 加速的原因是交付速度降下来了，增压压力材料不好，就这么回事。所以说很少的气候上升。但关键是交付我知道，所以说这个产，那你这种产品就1毫米，你加了8毫米的交付没意义，你最多就是1毫米，就是这个意思。你在你这个产品，比如说你产品2毫米，你交付最多开2毫米。我们下午也会讲，就是你其实就2件事，熔炼、成型、凝固。熔炼我都要搞干净，先不管。成型的时候只跟速度和粘度，跟什么都没关系。现在我帮你粘度提起来了，你只能改的就是速度。你要改速度，速度是为什么重力胶助为器？速度慢呀，要不就少1米，压住40米，你怎么打这个孔？我下午都讲，其实就是你举个例，咱就说对速度，咱说这么回事，你肯定是交付的速度越低，越不容易卷气。
The JF advised this one, right?
接下来是在交付后的时候，你要传递压力，你帮一下，你要压力传递，你后了好了，就这么回事。但为什么不做后呢？因为做后成本高呀，你要去啊，切不下来，切片机最多切到4.5，也不能做到极致。4.5毫米切片机能切下，剩下都是压力一定是不能是过流的，重力胶布一定是层流，慢慢灌进去的。我们在这个从1米到40米之间，胶布一般压是40米，从1到40米之间到底是啥？你找什么要做？根据你的产品，产品1毫米，慢慢灌，你灌到哪？
To the previous slide. These videos will need
Need to click, right?
click on each.
Okay. So manually. Okay. Or just these two, right? Not the middle. Okay. So this clip.
没有人愿意说，你说这个问题是甲方，你让他降价，他有车之后他经销为什么上？那谁挣钱？还有呢，如果我是药厂，我就希望维持越短越好，因为甲方付钱的，好多事情你讲不成。
So you gonna got the clip here. This forward, this backward.
This is forward.
Yeah. For the next.
Okay. Point. Is there a pointer?
Yep.
Okay. Perfect.
你不是你身份多大吨位？比如像我们这个10万200万，800吨的模具大概20万。最少20万，还不得华贵，这个华贵20万买不下。你再买好点，到20万还买不下来，太轻了。不到。那你模具是不是低啊？100万。我们全球的定价。对。好了，如果说你想想啊，像我们好多，如果说你100吨去做一个活啊，你量100之后，首先你的接盘会快，你流过时间肯定短，然后你的喷涂时间肯定短，对不对？你通过一使，你的轮廓你把电路弄个电，我可以把这个设备连起来。如果说你或者我免费给你租赁，没问题。如果说这个设备这个产品的这个价格单你给我，不愿意的，我们开清楚。价格不是随便定的。因为我看了你设备在那里。他们不会用，真不会用，没有几个人真正理解到这个东西是干啥。其实我们更多的是降产，我们不是说是从产品的性能、产品的质量的好坏，对吧？这你那个外观件，你更关键的是包括这个芯片下面是吧？那这样肯定有错误，不是谁家做的，那是必然的。然后你让他扫那个扫 CT 的时候，我们综合孔隙率是比它低的，价值。那这就是价值，特别是小的，越大越明显，越大越明显。后面听完怎么分析？后面好了，我一合等于说。我是机子公司的，我不是代理，都是我是。你是在我在中国。股东。这我们打的这一块高。
是你们应该多做一些这个技术的培训，用的
我们培训太多了，
国内有吗？但是
国内我有8个台 L 用起来，我们现在在欧洲，在美国做。
这是个问题啊，各个行业有光棍都不知道，
我们 iPhone 也是做的，
这是大问题啊。
我们都培训了，也讲不明白。是的，我也给他讲。他不希望我们介入到跟甲方合作，他要我转述给他，他转给他，他不会让我们去切入他的产品。
假如说我们有新项目对吧，在研发阶段能不能一起
我告诉你，我们在和爱心的体验营，我们和爱心的他也知道，我们帮客户一起创，还是做出，然后找供应商，但是我要没有说啊，我要自己来讲。没关系，我就不会啊。是这样的，我们就这样讲。
应该这样，对吧？
听听，下午听听，你刚才问的所有问题，下午都有答案。完了，我们再联系，再讨论，没问题。没事，您客气。我自己做了10年了，高物项我做了5年，一共做15年。我的研究院原来在北京一直经常干，因为研究那个高物项。
所以你以前是在什么？是你们学习？
对，我的研究院每天当 treat 的。มีคนเดี๋ยวโทรมาก็ส่งเป็น invitation อ๋อใช่ผมมีอะไรอยู่มั้ง
所以你认识这个杨教授你是知道的啊？对啊。
然后我认识国内包括国外整个这个都办公室，他们都认识，因为我们辽大朱强，
朱强对。
周文是我老大，我们还一个团队的。
哦。
他在南大。
对南大。
对他。
如果是。
他是他原来我们我博士毕业的时候，刚好到5000-2000人吧。我们在研究院一起到里面，我来自我家里就是读书，这是我有故事。我2016年为止，我在研究表，然后呢，我们把那高度项转给李宝山新嘛，后来卖给埃克比亚的。1号洞那是我带他去买的，我带他去加拿大买的。对。
这两个这个一个导弹
就是康泰哦，康泰的话，对康泰它的那个又是另外一种方法，它是做一个像化一块化掉，浇一个小块，它拿出来。那个是谁？那是润兴泰自己仿的，然后我就知道。润兴泰，珠海润兴泰。对，就李谷南他们给他们仿的。找到北科大的那个。毛老师。
这个是他们自己。
哎，他们自己仿的。
就把那南派去掉。
对。这是真认识，我很少在国内讲，没必要。
所以这两种哪个？
它又不一样的，就是。
一个是那
不是，它那个角度嘛，首先你最好别乱动，别动在上面。你只要角度。一定是这个角度。对。
但是他们现在是用那个什么真空的方法。
那越整越复杂了，那他们咋生产呀？
这个应该是不是很复杂？
我知道，那真空下，你整个生产成本搞得越高。我们特别喜欢做加法，我们一直在做减法，我就帮忙就完事了，3秒。就真是这样的。还有一个就是，他那种方法，他对那个材料是有限制的。他们是半固态，我们叫 superheat slurry，我们是热水里面有固态。我问你啊，我们平时说，工业混合物不是这个0度，有水混合物是0度嘛？你必须降到1线线以下嘛，你才有固相嘛。我们不是，我们是热水里面。那是非平衡状态。
急速的这个。
对，它其实你是问的时候，它是液态，你其实测的它是液态，但它里面有固相。我们无论是做高固相还是低固相，它都会降到1线线以下。它叫equivalent，它是平衡态的半固态，工业混合物嘛，它平衡了已经。我们是不平衡，叫non-equivalent，是热水里面有平衡。你说是不是半固态？各位选说这就不是，因为有高啊，是液态。
但实际是有固态。
实际是有固相的。这就是这个技术，它在8成一个 MIT 它最大的发明就是这个superheat slurry可以。但是我降到1线以下就半固态了。我把那个 superheat 那一段的 superheat 我降到1线以下，因为我一倒到吊桶，倒到模具，自然就降到1线以下，所以说就是半固态。它在冲击的过程，前面叫 superheat slurry，只要开始往前走，冲击的过程变成3D solid，它最后增压结束。这个不太一样。还有呢，它不是在勺子里面做半固态的。你把固相率20%，你说你倒的干净吗？这都是骗人的。勺子里面如果是20%的固相，稠的，你能把你那个给汤那个勺子倒干净，你没法那样产，做实验没问题的。 少粉，他老说他的功效率20%，不可能，20%倒出来，我试试，你给我倒一个4个温。小对呀、你每次倒料的重量都固定不了，标准速度都控制不了。我们不是，我们制浆蓄力它是液态，它是高温，它液态以上，它跟液态一样。我带着小米稀饭倒的料头，倒料头就变成了你要的目标值了，然后一速半速效果就小，不一样，对吧？对，好。 就给你电话号码和姓名，你的姓名对不对？更新我的这个15861662977。
Can you open this one on the screen now? Because I can, so because this is the next one. So
Okay, I will tell him. เขาให้เปิดเพลงเขาจะให้เปิดเพลงคือก็เมื่อกี้คนนี้เขาบอกว่าให้เปิดสไลด์เขาขึ้นให้แล้วได้เลยใครให้เปิดเพลงสักทีมงานดิสโก้เขาจะให้เปิดเพลงพอเบาๆมันคนละกันหมดเลยเขาแฟร์ไดร์เขาขอแฟร์ไดร์เขาเทียบให้เอาอะไรนะครับเขาอยากให้เปิดเพลงเบาๆค่ะมันอยู่เครื่องมันเป็น KV ใช่ไหมเครื่องมันเป็น KV อยู่ใช่ไหมตอนนี้ใช่ไม่ใช่มันคือการเซฟแล้วคือการเซฟกูใช้เครื่องกูไม่ได้แล้วเพราะว่าเขาพอยเด้งคือกูเซฟทุกอย่างในเครื่องกูหมดแล้วก็คือตอนที่จะเอาสับไปเครื่องนี้แม่ก็ไม่มีเพลงเครื่องนี้ก็ไม่มีเพลงไม่เครื่องกูเปิดเอาแล้วเอาไมค์จ่อได้ป่ะให้นะเพื่อนเขาเข้าอะไรคาตาลีหรอไม่ใช่YouTube มันอยู่ไหนไม่เข้า YouTube สักทีอ๋อมึงมีอันนี้แล้วอ๋อมันแอปดนตรีจัดมันจะเสียงไปออกไหนวะอ๋อแล้วตัวแปลงก็เสียบไปนี้อยู่จะเสียบเข้าสายเสียงไม่ได้ไหมได้ดิก็ไม่ได้เสียบอะไรต่อไม่ใช่หรอได้ไหมไม่นั่นแหละกูจะบ้าทุกอย่างเสียงมันจีแล้วคือจะวางยังไงได้สายเสียงดึงให้เราแล้วมันกองกดหรือไม่ใช่ไม่ล็อกไว้แล้วทำไงทำได้เป็นยกของอาจารย์เสียขึ้นเจือจางน้ำไงยับคือกูไม่รู้ว่าใครมีอะไรบ้างเมื่อกี้ก็สดก็น่าจะแบบ20 กว่าแต่ปะก็ทักมาเดี๋ยวกูเข้ามาแต่ไปเพราะข้างหน้าน้องก็ทำได้แหละแต่ว่าก็มีอาจจะช้าหรืออะไรนิดหน่อยเพราะว่าเดี๋ยวมันต้องไอ้นี่ได้ไงอะไรนะภาพ KB แม่งก็อยู่ในเครื่องกูก็ขี้เกียจอ่านเปิดเครื่องนี้ไม่ได้เซฟแล้วทำไมต้องใช้อาจารย์เจตเปิดทำไมออกฟอนเด้งมึงมันไม่มีฟอนต์ ฟอนต์แล้วเปลี่ยนตรงนั้นเลย สมมติว่าสมมติใช้ฟอนต์ ABC ใช่ปะแต่เครื่องมึงไม่มี ABC แล้วพอเขาเอาไปลงปุ๊บอะฟอนต์แม่งเด้งของมึงที่ ABC มึงก็ต้องกดตัว ABC แล้วโหลดฟอนต์ทำทุกอย่างตรงนั้นเลย
มันสามารถโหลดเป็นไฟล์อะไรสักอย่างได้
ทำ PDF ได้แต่ PDF มันมี
ไม่โหลด PDF มันเป็นวิดีโอไม่ได้ไง
ใช่เป็นวิดีโอหรือว่าเป็นอะไรเคลื่อนไหวเนี่ยมันทำไม่ได้